This is section 10.2, and we'll be talking about arcs and chords. First, let's start with the definitions for some arcs. We have a minor arc, and a minor arc is going to be a small arc that travels along the circle. An arc is just an unbroken fraction of the circle, and this is the small one. We would call that one arc AB. Now, there's another arc that starts at A and ends at B. It would start at A and go around in the other direction and eventually end up at B. That's considered the major arc. And the way we distinguish between them is we put a letter in between, so I could call this major arc, arc ADB. If you only see two letters, then you assume that you're talking about the minor arc, the shortest distance, whereas for three letters we have to put them in there to show which direction we're going. If I wanted to put another letter in here, I could also call that minor arc, arc AEB, and that would be accurate as well. But we have to use at least two letters and no more than three letters. The third term that we have is semicircle. Semicircle is half of the circle. AC would be a semicircle. However, I don't know which AC we're talking about. Are we talking about the AC that's going on the left-hand side and going counterclockwise, or the AC on the right that's going clockwise? So for this semicircle, I need to make sure I'm specific enough. And if I call it ADC, then I'm talking about this one on the left. It's going halfway through the circle. Semicircle will always have endpoints that are on the circle, and if I connected those those points together to make a segment, that segment should pass through the center of the circle, making AC then a diameter. Angles. We have two different kinds of angles we're going to focus on. The first one is the central angle. The central angle would be when you have the vertex of the angle as the center of the circle. That's why it's called the central angle. And then the endpoints of these rays would have to intersect on the circle as well. So if I call this angle 2 would be an example of a central angle. Whereas an inscribed angle has the endpoints on the circle, however the vertex is going to be on the circle as well. So this would be an example of an inscribed angle. Angle 3 is inscribed. Next, when we're talking about arcs and we're talking about the measurements, I would say that the measure of an arc is equal to the central angle that has the same endpoints. And here's what we mean by that. If I put a point here A, a point there B, and I'm going to put the center of the circle in there at C. Angle ACB is a central angle, and the measure of angle ACB is equal to the measure of arc angle AB. So the measurement of that arc angle. Now, there's a couple ways we talk about arcs. There's an arc length and an arc angle. What we mean by this arc angle is if you were starting at point A and maybe facing in towards point C and you started rotating around the circle to get to point B, how many degrees did you rotate around that center point? If you started at A, went all the way around the circle and ended up back at A, you've been rotated 360 degrees, and that's what we're talking about with this one, the measure of rotation for that arc angle. Next, two chords are congruent if and only if their midpoints, if and only if their midpoints are equidistant from the center of the circle. So if I have a circle, and here is one of my chords, I'll call this chord AB, and its midpoint would be right there. And if this is chord CD, and it has the midpoint right here, and these two chords, A, B, and C, D, would be congruent. They would have the same length if this red distance is the same as this green distance. Two chords are congruent if they're equidistant from the center of the circle, and we find that distance by going from the midpoints. This is the perpendicular distance. Those two segments would have to be congruent to each other. Next, a diameter bisects a chord if and only if it is perpendicular to the chord. So here's our circle, here is my chord, and I'm going to have my diameter come in. It's going to bisect the chord. It's going to make these two segments congruent to each other. So this diameter is bisecting chord AB. It also means that it would be perpendicular to it. In order to show that's true, I could draw in this orange segment, and I can draw in this orange segment. Now we know those would have to be congruent to each other because they both represent the radius of the circle, and this segment is congruent to itself starting from this center point to this intersection point. Those two segments would be congruent to each other. So if I knew that the diameter was already bisecting segment AB, then these two segments are equal to each other, meaning by side, 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 the triangles are congruent. Corresponding parts, this angle congruent to that angle. They also form a linear pair, so they're also going to be 90 degrees. And we could do that proof in the reverse order to show that if this is a right angle, then also those two segments would have to be congruent to each other. Another definition that we have, or another theorem we have for congruent chords, is that two chords are congruent if and only if their intercepted arcs are congruent. Okay, what do I mean by that? I have chord AB and chord CD. These chords are congruent only if their intercepted arcs are congruent. So if I draw in this segment, draw in that segment, if the measure of arc angle AB is equal to the measure of arc angle CD, and draw in these segments as well, that would mean that angle 1 and angle 2 are equal to each other. The measure of arc angle AB is maybe 80 degrees. Measure of arc angle CD would also be 80 degrees, so measure of angle 1 and measure of angle 2 would both be 80 degrees. So if this is true, we know that those central angles are congruent to each other by the definition. The radius of a circle can't change, so this segment congruent to this segment, congruent to this segment, congruent to this segment. So this triangle is congruent to that triangle, so by side angle side, the triangles are congruent, which means that segment AB is congruent to segment CD. It is a biconditional, so I could have started by saying that these segments are congruent to each other, and if I had segment AB congruent to segment CD, I could still prove those triangles congruent, then by corresponding parts, then I could say that this central angle is congruent to that central angle. By definition, then, measure of arc angle AB equals this, measure of arc angle CD is equal to this, then through a transitive, measure of arc angle AB equals measure of arc angle CD. Next question. Is line AB a tangent? Well, one of the properties we learned about tangents yesterday as it applies to circles is that this tangent, if it is a tangent, BA, would have to be perpendicular to this radius at the point of tangency. If it is a radius, that means that this would be a right angle. We're not sure yet, so we're going to check the Pythagorean converse. Is 4 squared plus 12 squared equal to 16 squared? Unfortunately, it's not, which means that even though AB looks like it's tangent, it definitely is not, because the Pythagorean converse didn't work. So is this a tangent? No. Last one more example. We have this given diagram. It's called circle R because R is the center of the circle, and we have to find all of these different angle measurements. This central angle is 20 degrees, which means that this arc angle is going to be 20 degrees also. We have a right angle for the measurement of angle CRB, which means its corresponding arc angle is going to be 90 degrees. AB is a diameter. The way I know it is because its two endpoints are on the circle itself and it passes through the center. So this BCA or ACB is a semicircle at 180 degrees. This is going to be 90 degrees on the left. And then we have another right angle down here. Measure of angle ARD is 90 degrees. So measure of arc AED is 90 degrees. This little part is 20, so this angle is going to be 70 degrees. And then one more time, we have a 90 degree arc angle over here. First question, what's the measure of angle ARE? Well, since this arc angle is 70 degrees, that means that this central angle is going to be 70 degrees as well. Measurement of angle DRB, we're talking about this central angle, that's going to be equal to 90 degrees. Measure of arc angle DE, so starting at D, rotating around the point E, is going to be 20 degrees because the central angle is 20 degrees. Again, we assume that we're going for the shortest distance when there's only two letters. We're not going all the way around. We're starting at D and going the shortest distance to E. Measure of arc angle EAC, starting at E, going to A to C, we have 70 plus 90 or 160 degrees. Measure of arc angle EBA, starting at E, through B, ending up at A. We've almost gone around the whole 360 degrees. In fact, we're just 70 degrees short of that. So 360 minus 70 tells me that this must be 290 degrees. Measure of arc angle AB, 180 degrees this way, 180 degrees that way. It's a semicircle, so it's got to be 180 degrees. Measure of arc angle CE, where we want the minor arc because there's only 2 letters. The shortest distance is going to go in this direction, so it's 90 plus 70 more for 160 degrees. And lastly, the measure of angle C, arc angle CBE, starting at C, through B, ending up at E. That's 90 plus 90 plus 20, which would be 200 degrees.